Hey everyone, today we're going to get right into the heart of chemistry. We're talking about the basic ideas that, well, they make up everything. Seriously, the air you're breathing, the device you're watching this on, it all comes down to chemistry.
I absolutely love this quote by Roald Hoffman. It just nails it, right? It tells us that chemistry isn't just a list of elements to memorize from a textbook. No, it's a creative science. It's about being a builder, a creator, and making things transform.
Okay, but transforming molecules? That sounds a bit abstract, doesn't it? What does it actually mean for you and me in our daily lives? Well, that's exactly what we're going to unpack today. We'll look at what chemistry really is, why it matters so much, and trust me, its history is fascinating, and the simple rules that run our entire world.
All right, so here's the game plan. We'll kick things off with what chemistry actually is. Then we're taking a trip back in time to ancient India. It's an amazing story. After that, we'll cover the basics of matter, and finally, we'll dive into the chemist's toolkit and the rules of the game.
Okay, let's dive right into our first section. So what is chemistry anyway? Let's get a super simple definition on the table.
Basically, you can think of chemistry as the science of stuff. Anything and everything. It's all about asking three simple questions. What's it made of? What are its properties? And how does it change? You see it every day, right? When milk turns into curd, or when a piece of iron gets all rusty after a monsoon shower. Yep, that's chemistry, right there in front of you.
Now, this is the part I find absolutely fascinating. Chemistry isn't something that just popped up in a modern lab. To really get why it's so important, we can travel way, way back in time, right here to ancient India. The history of chemical discovery here is just incredible.
Just look at this. This isn't just a timeline. It's a story of human curiosity. We're talking thousands of years ago, in Harappa. People were mass-producing perfectly baked bricks. That's controlling chemical reactions. Or look at the Vedas, where they describe processes for tanning leather and dyeing cotton. This isn't just history. This is applied chemistry happening for centuries.
And it gets even more amazing when you look closer. Our ancestors had a name for it, Rasayan Shastra. How cool is that? The science of chemical essences. They were masters of metallurgy, pulling metals like copper and gold from the earth. They could make gunpowder, strong acids, and get this, they even invented soap. A big shout out to Chakrapani for figuring out that mustard oil and alkalies combo. What a legacy, right?
Okay, so from that amazing history, let's switch gears and get back to basics. All this chemistry, all these transformations, they happen to one thing, and that thing is called matter. The definition couldn't be simpler, but it's so powerful. Matter is, well, everything. The phone in your hand? Matter. The water you drink? Matter. Even the air you're breathing in right this second? You guessed it, that's matter too. As long as it has mass and takes up some space, it counts.
And this stuff comes in three main flavors, or states. Think of solids. All the tiny particles are packed together super tight, like people in a crowded bus. They can't really move. Then you have liquids, where the particles have a bit more room. They can slide past each other, which is why liquids flow. And finally, gases. Well, their particles are like kids in a playground, just running around freely, filling up whatever space they can find.
All right, so we've got matter, but the world is full of so many different kinds of matter. So how do chemists organize it all? Let's break down the building blocks.
So it really comes down to these three main groups. You've got elements, the purest stuff, like pure copper or oxygen. Then you have mixtures, which is just a mix, like adding salt to water. You can still separate them pretty easily. But compounds, oh, this is where the real chemistry magic is. Think about this. Hydrogen gas is explosive. Oxygen gas helps things burn. But when they chemically join together, they make H2O, water, the one thing we use to stop fires. Now that is a transformation.
Okay, to study all these amazing changes, scientists needed to be able to talk to each other. They needed a shared language, a universal toolkit for measurement. So let's see what's in that toolkit.
And this is so, so important. Imagine the confusion if everyone used different measurements. The SI system fixes that. It's the standard. So a kilogram in Mumbai is the exact same kilogram in Tokyo or Toronto. It makes science a global conversation. Here are some of the most important units we use.
But here's a problem, a huge one actually. These units are great for things we can see and hold, but what about atoms? I mean, how on earth do you count the number of molecules in just a tiny bit of something? For instance, in just 2 grams of hydrogen gas, you have, well,
that many molecules. It's an impossibly big number. You obviously can't count them. So chemists had to invent a shortcut. And that clever shortcut is called the mole. Now I know it sounds a bit strange, but stick with me. It's just a counting word. Like when we say a dozen eggs, we mean 12. Or a pair of shoes, we mean 2. A mole is just the chemist's version of a dozen. It's a word that means a specific, very, very large number.
And this is the number. It's called Avogadro's number, and it is just gigantic. It's a 6 with 23 zeros after it. It's almost impossible to wrap your head around. But this is the key. This number is the magical bridge that connects the tiny, invisible world of atoms to the world we live in, where we can actually weigh things in grams on a lab scale.
All right, so we have our building blocks, matter. We have our toolkit, the mole. Now for the final piece. We need to understand the rules of the game, the laws that tell us how all of this stuff actually works together.
And these laws, discovered over a long, long time, changed everything. They were total game changers. They showed that you can't just create matter out of thin air or make it disappear. It just changes form. And they proved that compounds, like water, always have the exact same recipe. Always. Suddenly, chemistry wasn't some mysterious magic anymore. It was a science with rules. These laws paved the way for our entire modern picture of the atom.
This idea of predictable recipes leads us to this big word, stoichiometry. I know, it sounds super intimidating, but honestly, all it means is chemical math. It's like the recipe for baking a cake. It tells you exactly how much flour and sugar you need to get the perfect cake at the end.
And here's how it works, broken down into 4 easy steps. First, you write out and balance your recipe, the chemical equation. Second, you convert everything you know into our favorite unit, moles. Third, you use the recipe's ratio to figure out what you need. And finally, you convert your answer back into grams or liters, something you can actually measure. That's the whole process. Simple, right? So let's just step back for a second. When you look at the whole picture, you can see this beautiful, clear line connecting the past and the present. It goes all the way from the ancient practitioners of Roscion Shastra working with metals and herbs to today's scientists in high-tech labs. At its heart, chemistry has always been about one thing: understanding the world around us so we can shape it. And that brings us full circle, right back to that first idea. The chemistry is creative. It's about building. So I want to leave you with a question to think about. Now that you know the basic rules of the game, if you had the power to design and build any molecule in the world, what problem would you solve? What would you create?